Hey, welcome to the 27th class meeting of EECE574, the graduate level probability and random processes. As usual, homework will be assigned, so you need to find it. Here goes the overview. We are covering the temporal characteristics of random processes part. So our most of the interest is in the correlation functions, and we are going to study that today. Let's review what we learned last time. So the topic of last class meeting was the complex valued random processes. It could be a scalar valued or vector valued. First, when we have a single complex random process, you have to think about it as what? Two random processes are given. Got it? So since the real part is a real valued random process and the imaginary part is another real valued random process, in principle, you are given two real valued random processes. For the full characterization of single complex random process, you need to just do what you have done to completely characterize jointly distributed two real random processes. So by using the Kolmogorov's idea, you sample M, you take M samples from real part, you take N samples from the imaginary part, and then you form a big random vector consisting of two random vectors. And then if you can find any joint characteristic, joint PDF, PMF, or CDF or characteristic function of that random vector, you are done. So that is the idea of full characterization. Then what is stationarity of a complex valued random process? Stationarity is also based on the idea of stationarity of real and imaginary parts. So when do we have two random processes stationary? Again, Kolmogorov's idea. We take M samples from real part, N samples from the imaginary part, and then we consider joint distribution. And if the joint distribution is invariant by any time translation, then the two random processes are stationary. Since this full characterization and strict sense stationarity is too restrictive, so what do? Usually, we consider wide sense stationarity over complex random process. So here goes the definition. The problem is that given a single complex random variable, we have two correlation. First is the kind of ordinary correlation where we calculate the, so we have two covariance functions defined as x of t1 minus expected value of x evaluated at t1 times x of t2 minus the mean of x evaluated at t2 conjugate. So this is the kind of ordinary covariance function of a complex random process x. But we also have pseudo covariance function where we don't have conjugation. So we need two correlation functions. The problem is that people didn't much pay attention to this complementary or pseudo autocovariance function of a complex random process. So they defined wide sense stationarity only in terms of this ordinary covariance function. So most of the definition says if mean path of a complex random process is constant for time t, and if the ordinary covariance function is a function of only time difference t1 minus t2, then they define the complex random process wide sense stationary. However, since some people found the complementary covariance is very important, especially in communications or radar engineering, in which field man-made signals are more dominant than the nature-made signals, we have this complementary covariance function does non-vanishing complementary covariance function. In that case, some people put the constraint on the complementary covariance function again, like complementary covariance is a function only of T1 minus T2. In that case, this second order stationarity, which shouldn't be confused with the stationarity to order 2. But second order stationarity requires mean pass constant, autocovariance function of time difference, and complementary autocovariance function, again, function of time difference. And also, since we handle complex valued random variables, uncountably infinite, we also want to define proper complex random process and improper complex random process. The definition is very simple. If the complementary covariance function is 0 for all T1 and T2, then the complex random process is called proper. Otherwise, it is called improper. By the way, this part is not proven, but asked you to try this. And it says that if you have Y-sense stationary real-valued bandpass random process, then its complex equivalent random process is always proper. So if you are a radar engineer, if you are a communications engineer, especially in physical layer, then try to prove that. Let me repeat. So the question is this: given a Y-sense stationarity real bandpass random process, is its complex baseband equivalent random process proper? So let's say, given a Y-sense random x of t, let's say complex baseband equivalent process as z of t, which means that x of t equals real part of z of t e to the j 2 pi fct, something like this. Got it? And x of t is real Y-sense stationary bandpass, and z is complex baseband random process. And what is most important is that if x is Y-sense stationary, then z is proper, especially zero mean proper. Anyway, now let's consider the cases where we are given 2 complex random processes. Then actually we have 4 real-valued random processes jointly distributed. And stationarity, full characterization, and joint Y-sense stationarity, other things are just straightforwardly extended. What about the case where you have complex valued vector random process, where you have some capital N complex random processes consisting of this vector complex random process? Again, the definitions are very simple. You can define the mean pass, you can define the autocovariance function, you can define autocorrelation function, you can define complementary or pseudo autocorrelation autocovariance functions. Of course, you can talk about propriety, you can talk about second order stationarity, everything just extends. And as we've seen in this section 6.7, as far as you remember the Kolmogorov's theorem, then you can always rely on that theorem to understand what's going on. So I believe the Kolmogorov's theorem is one of the most important theorem for you to understand, to deal with random processes. Now, here goes the section 6.6, where we talk more about correlation functions, not only the autocorrelation, cross-correlation, complementary correlation, and complementary covariance functions. The first thing related to talk about autocorrelation function of random process is, first, we divide the entire set of random processes into finite power random process and infinite power random process. So here goes the set of all random processes. And of course, there is very small subset, but in order to exaggerate, because it's useful, we just divide it into two. So here, finite power random process and infinite power random process. By the way, what is the definition of the finite power random process? If a signal is deterministic, in order to calculate the power of a deterministic signal, what you need to do is that you take the absolute value and square. That gives you the instantaneous power. Sometimes you talk about that, or sometimes you take the time average and divide by the period of time. That is kind of time averaged average power. But here, the finite power random process is defined in terms of the instantaneous power. So if this is finite for all t, then the random process is called finite power random process. And you may say that, what's the use of this infinite power random process? There is a class of random processes called finite random processes, where you have infinite power. And the definition in the time domain is very simple. Your sample taken at t1 and your sample taken at t2. So your x of t1 and x of t2 if it is complex, of course, you need to take the conjugation, and then you take the expectation, which is simply the autocorrelation function. That is what? That is proportional to delta of t1 minus t2 and times something. And that something is either constant or function of what? t1 and t2. So you may say that, okay, I just introduce some function of two parameters t1 and t2, then this would be the definition. And here you can easily see that if t1 is different from t2, then the correlation is 0. However, if t1 equals t2, what happens? In that case, this becomes infinite, and you may say that what's the use of this one? But if you want to integrate this autocorrelation function, actually this does matter. So here, anyway, when you integrate t1 equals t2 case survives, so you can just say that, okay, I'd better use a single variable function, q of t1, or if you want q of t2, it doesn't matter because you have multiplication with the delta of t1 minus t2. Anyway, so this is the definition of a white random process which has infinite power. See that? This is what? This can be rewritten as expectation of x of t1 and x of t1 conjugate, which is x of t and x of t. So it's autocorrelation function of x evaluated at the same time instant. And see that in this case, whatever t you have is finite, right? So you may say that, okay, this may be sum to tilde of t, depending on the time, the same time instant, right? And if you compare with the white noise, what's the difference? If t1 equals t2, this is finite, but this is infinite. Got it? So in that sense, we have just defined a white noise. And the reason why we call it white becomes clear when we, after we study the notion of power spectral density over random process. Got it? So we have defined this too, and you may wonder why we define this one in order to talk more about the correlation functions, because only on this subset, most of the arguments make sense, okay? So if I'm not teasing you in the final exam, probably I will never ask you what will happen about the autocorrelation functions in this subset. Usually, I will ask you what happens on the correlation functions here when you are given finite power random process or finite power random processes. Got it? So that's why last time we defined the finiteness first. Okay, so finite power process, and also we define white random process. Now, here goes, just a second, yeah. Here goes a very important example, which appears here and there or everywhere when the authors of textbook wants to, how to say, break your, how to say it, some prejudice, yeah, on the result. So just think about the ensemble, which contains all the sample paths of this random process. Here, we intentionally fixed A and F0, which is non-zero, to make the situation more simple. And here, theta is a uniform random variable from 0 to 2 pi or any continuous 2 pi or modulo 2 pi interval. Now, if you calculate the mean path, what do you have? Amazingly, even though each sample path is a cosine function with some phase shift, your mean path is always 0, right? Because of this theta. And not only that strange thing, but also your autocorrelation function becomes what? Becomes periodic function only of tau. So this random process, even though its sample path is always cosine function, is Wisen stationary. And under certain conditions, on A and not only A and not only theta, but if A is the random variable, blah, 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 and sometimes you can show that this random process is strictly stationary, something like that. But anyway, in this case, it's not strictly stationary, it's Wisen stationary. And it says a lot of things. First thing is that, as we've talked about it repeatedly, mean path or mean function, even a mean function may not be a member of the ensemble. So the mean path can never be a sample path. Got it? And this shows it. And another thing is that even though the process is Wisen stationary, it could be deterministic random process. And third is that here, as it is specified, autocorrelation function can be a periodic function. And some of your neurons in the brain says that, okay, if the autocorrelation function can be a periodic function can be decomposed into sines and cosines. So it seems that any function can be an autocorrelation function over random process. That is not true, okay? And here we haven't yet proved, but here goes one of the most important theorem. The autocorrelation function over Wisen stationary random process cannot take an arbitrary shape. And this shape becomes more clear after we study the power spectral density. But at this moment, just to keep in mind that the autocorrelation function cannot be of arbitrary shape. However, even though we haven't yet studied the frequency domain characterization of a random process, still we can say a lot about the autocorrelation functions. So here goes some results. Suppose X is a real random process, which means that X equals X conjugate. Now, what is the autocorrelation function? The right-hand side is simply expected value of X of t plus tau times X of t. And the left-hand side is what? According to the definition, see that? When we say that the random process is Wise and stationary, we choose two arguments and subtract the right one from the left one. That is the convention we just to take. So here, what does this mean? Either you change tau to negative tau, or you add tau on the right side. So let's take the second case. So left-hand side is by definition expectation of X of t times X of t minus tau, right? So if X is Wise and stationary, if you subtract left, if you take left minus right, then you have, just a second, plus tau, sorry about that. Yeah. You have negative tau, right? But due to the commutativity of the multiplication, this argument of the expectations are the same. What does that mean? They must be the same. So in this sense, what do you have? The autocorrelation function of a real Wise and stationary random process is a symmetrical function. By the way, here, even though I said Wise and stationary, the lemma says at least Wise and stationary. What does that mean? Of course, not only Wise and stationary, but also it could be second stationary to order 2, stationary to order 3, blah, 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 everything, which implies Wise and stationarity, okay? So under any condition that implies Wise and stationarity of real random process, the following lemmas hold, something like that. So first thing is that the autocorrelation function must be a symmetrical function if X is real. What if X is complex? Let's say Z. Then can we say that the autocorrelation of Z is real even? Of course not, because the definition does not allow commutativity due to the conjugation. So even though you change the order, you have conjugation still persist. So what does this mean? Actually, you have what? Conjugate symmetry of the autocorrelation function if Z is complex valued Wise and stationary random process, or at least Wise and stationary random process. It could be second order stationary, but anyway, second order stationarity implies Wise and stationarity. So the extension of this lemma to complex valued random process is that autocorrelation function is a conjugate symmetrical function of tau. Now, let's go back to the real value case. So if you want to draw an autocorrelation function as a function of a single parameter tau time difference, then you have some symmetry. And the second one gives you a more restriction on this symmetrical autocorrelation function and says that your autocorrelation function can take positive value or negative value. It doesn't matter in some cases, but its absolute value is always bounded by autocorrelation function evaluated at 0. So here goes Rxx0, and here goes negative Rxx0. By the way, how can I be sure about positivity of autocorrelation function evaluated at 0? How? Because whether X is real or complex autocorrelation function evaluated at the same time instance, right? Is what? This is simply X of t squared. And expectation of something is something times its probability, and that something is always non-negative, and probability is always non-negative. So this is always non-negative. That's why I wrote here. Okay. Of course, you may say that can it be zero? But in that case, if this is zero, what happens? Some random variable x has expectation of absolute value square of x equals zero. What does that mean? X is zero, or more surely, or probability 1. Right? So it doesn't matter. It's zero random process. So what do you want to say? So what I want to say from lemmas 1 and 2 is that if X is a real, at least wise and stationary random process, it is bounded by plus and minus, positive and negative, Rxx0, and it's a symmetrical function. Got it? You can take some negative value as some negative values as some tau. And can you say other things? Actually, it's not that easy, but from our example, that strange random process, a cosine 2 pi f0 t plus random variable theta, we know that a wise and stationary random process may have periodic autocorrelation, right? So here it says, if x of t has a periodic component, then autocorrelation function also has periodic component. This is somewhat strange, but let's think about this case. So x of t has a periodic component. What does that mean? It has some portion, says function, let's say x is somewhat confusing. Let me use a, okay? A of t plus some n of t. And here, I'd better use this decomposition, mu x of t plus x of t minus. First, let's add and subtract the mean path, and then group x minus mean path as one, and you have one deterministic function that could be zero function for all t or not. Think about the case where it is periodic with some positive period t. Right? Now, what is the autocorrelation function? And if you calculate the autocorrelation function, and if you assume this is at least wise and stationary, then what will happen? After some computation, you will see that due to this periodic component, you have periodic component in the autocorrelation too. Got it? That's what is written here. And lemmas 4, 5, and I believe 6. Yeah, okay. This example talks something we haven't yet covered, that is ergodicity or ergodicity of random process. So under certain conditions, we can talk more about the autocorrelation function. And this ergodicity is very special thing. So let me draw a Venn diagram again. So here is the set of all random processes. What's the size of the subset of wise and stationary, or at least wise and stationary random process? Infinitesimally small, right? However, let me exaggerate. So here goes the wise and stationary random processes. Okay. What about ergodicity? Ergodicity means something like this in a wide sense. Some people say ergodicity is inside this stationarity, but actually that is not necessary. So, okay, let me draw it small. So, some people say ergodic, but in English, ergodic is more popular pronunciation. And this subset of ergodic random processes has very special property. And this ergodicity in a wide sense, of course, it has narrow sense. Ergodicity means that definition is little bit vague in the wide sense. From a single sample path. And by taking a time average, and we haven't specified what kind of time average we take. We can extract some information about the random process. By the way, what is the information about random process? Of course, it's related to the first order, second order, third order, nth order CDF, PDF, PMF characteristic function. Also, that some information could be expected value. So mean path, autocorrelation function, some third order correlation function, fourth order, fifth order, that kind of thing. Got it? So why do we need this definition? It is because of what I told you already. In our mathematical definition, right? We can observe only a single sample path if our random process has sample path that expands from negative infinity to positive infinity. So mathematically speaking, if you define your observation time interval as negative infinity to positive infinity, you can observe only a single realization, single sample path. In that case, as I told you already, if you observe only once, probabilistic approach to handle uncertainty make no sense. Got it? So it's kind of strange thing, right? As we've seen already in the that strange cos, the constant times cosine 2 pi f0 t plus random uniform random variables data, that thing. See that? If you generate data, then this entire function is fixed. It's a cosine function with exact frequency and exact phase shift. What kind of random process does it make sense to take ensemble average of the sample path to compute the mean path, to compute the autocorrelation function? You may object to the idea of computing the expectation because anyway, precisely speaking, according to the math, according to your model, you can observe only a single realization. So ensemble average, which means the statistical average, doesn't make sense. So not just because of this mathematical rigorness, but also people have found that they have to they need to define some subset like this, where some interesting property holds that links single sample path and the entire ensemble. So they defined this subset and say that, okay, just take one sample path. However, from that sample path, you can still find, estimate, infer some statistical property of the entire ensemble. Not only the set of sample paths, but also how each sample path is selected. And actually, that idea looks strange, but actually that means each sample path actually, if you observe long enough, shows all the statistical relations between other sample paths, vice versa, got it? So even though it looks too restrictive, it's a nice property we need. Okay? Of course, there are many different definitions of ergodicity, strict sense ergodicity, or some very loose sense of ergodicity. So let's see some examples, but before we talk about that, anyway, let's go back to our topic of correlation and talk about some properties of autocorrelation. So suppose we have an ergodic and at least y-sense stationary random process X. And also assume that this mean path, which must be constant due to the y-sense stationarity assumption, is 0. Let's assume that. And X has also, we assume, no periodic component. So no periodic component, it's ergodic, it has 0 mean. Then, amazingly, your autocorrelation function, so you want to fill up these two lines, right? Using a curve, must what? Must vanish as you take tau to positive infinity or negative infinity. So you must have some function like this. Got it? And why I say this? Because we have no periodic component. By the way, the previous example we've seen has what? Autocorrelation function as a function of tau is periodic with period 1 over f0. Got it? So since this has periodic component in the autocorrelation, and actually each sample path is periodic, right? Even though its mean is 0. So it's what I claimed is not exact, okay? If its mean is periodic, definitely autocorrelation has periodic component. However, if its mean path is 0, still the autocorrelation function could be periodic. But anyway, so no periodic component, 0 mean, then you have this property. By the way, how can you prove? Actually, it's not easy. Okay? But if you, after you study again, power spectral density, you can easily understand what does this mean. And it is related to the Fourier transform. Okay? Anyway, so at this moment, just think about this. If it is not something direct delta involved in the frequency domain, what does that mean? If you have direct delta in the frequency 0, what does that mean? You have non-zero mean, right? You have constant function. So this is violated. So at f frequency 0, no component. What about periodic component? In the frequency domain, periodic component means that you have delta functions. So actually, this lemma 3 says that, lemma 4 says that you don't have delta functions in the frequency domain. Got it? And also we assume it's of finite power random process. In that case, due to the finiteness of the power, this holds. Your autocorrelation function must vanish as for sufficiently large tau. What does that mean, by the way? Since the autocorrelation function is a correlation between two samples, if your sample taken at some t plus tau and t are far away, which means that tau is very large or absolute value of tau is very large. So if you if you take two samples far apart and zero mean process, then correlation is almost 0. What does that mean? Two random variables are orthogonal. Got it? For sufficiently large separation. That's what it means. So as I emphasized repeatedly in this course, whenever you see limit something tends to infinity or 0, you must rephrase it as for sufficiently large something or for sufficiently small something. What does this mean? For sufficiently large sampling offset. two samples are almost what? Orthogonal, or how should I say that? If zero mean is uncorrelated, got it? Zero mean orthogonal means uncorrelated. Here goes another lemma. Again, we assume periodicity, which means that single sample path provides you information about ensemble average and statistical property. Here we assume now, differently from lemma 4, we assume non-zero mean, which must be constant due to the Weiss and stationarity assumption. Now, still we have no zero mean component, no periodic component. In that case, it's just simply you add non-zero component to previous random process. Now your autocorrelation is what? Some non-zero mean component plus zero mean component. And if you take this correlation, the non-zero mean component, whether it is negative or positive, becomes some positive squared or negative squared, which is always positive. So what you have is this one. See that? Due to this non-zero meanness, your autocorrelation function could be your correlation could be non-zero, even though they are separated far apart. However, that non-zero value reflects the square value of your mean path. So here goes an example. Suppose you have a second order stationary or stationary and ergodic random process x of t. So you have autocorrelation function only of tau. Suppose it is given in this way. Some constant plus 4 divided by 1 plus 6 tau square. And if you draw this one, if you draw the graph of this one, then what happens? Here goes 25, right? And then what is this one? It's similar to bell-shaped curve, but not exactly. But anyway, it looks like this, right? So it becomes smaller because denominator becomes larger, right? As tau tends to infinity or negative infinity. So what do you have? Here, you raised some Rayleigh PDF, something like that. So Cauchy CDF, sorry, PDF. And we already know that if tau is very large or very small, if there is no periodic component, what is this value 25? It's the squared value of your mean. But what is the square root of 25? You have two possibilities, plus or minus 5. So you have ambiguity in the mean value of the process in this case. It could be positive 5 or negative 5. But anyway. By the way, you can find the variance of this random process by removing the mean. Anyway, if you remove this plus or minus 5 squared, anyway, you subtract 25. So the variance becomes what? Variance becomes this height, which is 4 in this case. So 4 is the variance, which is what? X of t minus mu x of t squared. And then you take the expectation. Got it? Now, here goes something interesting for communications engineers. Since we use radio waves for wireless communication in modern electrical engineering, of course, we can use optical signal or infrared, terahertz, which is very different from radio and also different from optical signals. But anyway, let's focus on radio communication. In that case, what we do is that we generate a sinusoidal electrical signal and apply that to the passive element called an antenna. An antenna, similar to a loudspeaker or speaker that converts the electrical signal to an acoustic wave, the antenna converts the electrical signal to an electromagnetic wave, so-called radio wave. Got it? And if we just transmit radio wave, it is very difficult to put information there. Only the phase could carry information, but if you move away, then phase can change a lot. So what we do is that we modify the amplitude and phase of so-called carrier. The simplest approach was what? Just changing the magnitude. And in order to change the magnitude, what is the simplest is to use so-called radio frequency mixer. By the way, this term mixer is very differently used even in the same electrical engineering building. Some acoustic signal processing guys says mixer to imply adder. But RF engineers and communications engineers say a mixer to refer to a multiplier that multiplies carrier with some modulating signal. Okay? So carrier is modulated by x of t. Now the question is this one at this moment. What if x, that is the message signal in communication, can be well modeled as a Y-sense stationary random process? So suppose x of t here is a Y-sense stationary random process. Now you multiply the carrier in order to modulate the carrier. So your output y of t, that is still an electrical signal, which is x of t times cosine, in this case, omega 0 t plus theta or 2 pi f0 t. Then the question goes like this. Is y of t a Y-sense stationary random process? So first question is y of t Y-sense stationary. Second, if so, find the autocorrelation function. And the answer is very simple. Interestingly, y of t is also Y-sense stationary. And the autocorrelation function is also very interesting in the sense that it is modulated version of the autocorrelation of x. So here, if I remember correctly, something like this. Got it? And this 1/2 is from the fact that the power of cosine function is just 1/2. RMS power of cosine function is 1/2. So something like this, okay? And proof, you do it, got it? It's not that difficult, just use the definition. Y-sense stationarity of x of t implies mean of x is constant and its autocorrelation function is a function only of time difference. By using only these two facts, you can show that y of t is also Y-sense stationary. And your autocorrelation function of this mixer output is simply the input autocorrelation times 1/2 cosine 2 pi f0 t or cosine omega 0 tau. Okay, so we've done enough. Actually, we are going back to the autocorrelation functions later after we study ergodicity. But anyway, let's move on to the cross-correlation functions of two random processes. So suppose you are given two random processes, could be complex valued, x of t and y of t. First, what is the definition of a cross-correlation function? The cross-correlation function between x of t and y of t. The most important thing is that you need conjugation, okay? And there are many different conventions, but I personally prefer, and you'd better follow it because anyway, you are now MIMO age, MIMO generation of communication engineers. So you calculate a lot of outer products of random vectors where you need to compute expectation of x vector times y vector Hermitian transpose. So your conjugation related Hermitian goes right side factor. So here I put conjugation, and instead I give plus tau to the left factor. Anyway, so this is the definition when x and y are complex valued. If they are both real valued, you can ignore the conjugation. Now, what about uncorrelatedness now? Uncorrelatedness is not directly related to the autocorrelation. It's more related to autocovariance. So uncorrelated means that if you take the centered version of one random process, which means that you take the sample subtracted by the mean value at that sampling instant, and then you do the same thing for y, and then expectation of these two equals 0. So actually, uncorrelated means that this equals 0 for all t comma tau. Okay? Or if you want, for all t1 and t2. So here goes something strange. Let me see. Just a second, uncorrelated. Yeah, this looks correct. Why I do say this? Correlation coefficient is, yeah. Actually, you can show this is equivalent to Rxy t plus tau comma t minus mu x. Sorry about, we assume joint y and stationarity, so let me use tau only. Something like this, okay, if I remember correctly. Yeah. So if this is 0, what does that mean? The autocorrelation function is simply the product between the mean path of the random process. So you have this one, ready? Yeah, but just seconds, uncorrelated. Yeah, here we didn't yet assume at least y and stationary. So if y and stationary, then, so this is more special case. This is more general definition, okay? Two random processes could be uncorrelated even though they are not jointly y and stationary. So this is the definition, okay? By the way, independence implies uncorrelatedness. The converse is not true in general. Now, two random processes, they could be complex valued. So let me delete this part. Two random processes are orthogonal if their autocorrelation function equals 0 for all T1 and T2. Of course, you may define second order orthogonality and second order uncorrelatedness. So not only your cross-correlation function or cross-covariance function satisfies the condition for uncorrelatedness or orthogonality, your complementary cross-correlation and complementary cross-covariance function satisfy the definition. In that case, you may define them as second order uncorrelated random processes and second order orthogonal random processes. The problem when we talk about complex value random processes and their uncorrelated and orthogonality, people have just talked about the conventional, ordinary correlation and covariance functions only. That is problematic. Now, let's focus more on special cases where two random processes are y and stationary. Then, as we already know, autocorrelation function, a cross-correlation function becomes function only of tau. And if they are statistically independent and wise and stationary, we have what? This expectation becomes product of expectation. So left-hand side is what? Expectation of x of t plus tau and y of t conjugate. And if they are independent, we have what? Kind of factorization. And now let's assume they are wise and stationary, which means that this is constant. And this is also constant. So we are done. Okay. So this is a general complex valued random processes case. Okay. It seems that our handouts sometimes assume two real valued processes and sometimes complex valued random processes. So I will correct them to be more consistent later and upload it again. Now, here goes some properties of cross-correlation functions. And here, some properties are just simple extension of the properties of autocorrelation function. The question is why? Because you never forget this. You can just choose y as x. Then all the properties related to correlation functions must be what? The generalized cases of autocorrelation functions, right? So let's see. First, when x of t are real, wise and stationary real, just a second, let's see. So what is the right-hand side? Expectation of x of t plus, sorry, this is y, tau. So expectation of y of t plus tau and x conjugate of t. That is right-hand side. What is the left-hand side? Left-hand side is expectation of, so we have x first, xt plus tau, but negative tau, t minus tau, and y conjugate of t. Well, this is not true because we have on the right-hand side conjugation on x, left-hand side conjugation on y. So in general, they could never be equal. However, if we assume they are real valued processes, then what happens? Again, the right-hand side equals what? Rxy, xt plus tau, and left-hand side becomes Rxy, t minus tau and t. So without wise and stationarity and realness of x and y, we can say not much. However, since if we assume they are real jointly wise and stationary, then what happens? This becomes function only of tau, and which can be said Rxy negative tau. And here we have Rxy negative tau. So we have equality. Got it? So cross correlation between x and y evaluated at negative tau, which is the left-hand side, equals a cross correlation function of y and x evaluated at tau. So you just switch the order. So the sign of tau changes, flips. It's kind of obvious. Now let's take a look at the second one. And it may frustrating, but actually this is exactly what you've seen already. Just assume x equals y. What happens to the left-hand side? Left-hand side is simply the autocorrelation of x evaluated at tau equals 0. And which we've already seen that, which is the maximum after we take the absolute value. Got it? And what is the right-hand side? It's this is the autocorrelation taken, autocorrelation function after we remove the sign. What is the right-hand side? Right-hand side is what? The first term is Rxx0, and second term is also Rxx0. So you have Rxx0 squared after you take the square root. So the right-hand side is simply in the special case of y equals x, Rxx of tau is bounded by Rxx0. Got it? Which is positive. And we've already seen this, right? When we have a special case. And the third one may look frustrating, but it's not that frustrating because what is the right-hand side of the second property? Is the so-called geometric mean between two autocorrelation functions of x and y. So due to the geometric, arithmetic geometric means relation, which means that the arithmetic mean is always greater than or equal to the geometric mean, we have what? The right-hand side of the second property is bounded by the right side of the third line. So we in nature naturally have the third property. By the way, we could easily show the first and third property. What can we do to prove the second property? And that is again related to this one. And you've seen this, something similar. You can just say that, okay, if this is real, x is real, and y is real process, and alpha is real, what happens if you assume joint y's and stationarity between x and y? You have a function of quadratic function of alpha, where coefficients are all related to the second order correlation functions between x and y. And they are function of only tau. So since the left-hand side is always greater than or equal to 0 for all real value alpha, you can use the discriminant of this quadratic function to say some property. That is the idea. And that is just a pure mathematical idea. You've seen already when you showed that the Pearson correlation coefficient is bounded by 1 and -1, right? However, I emphasize that this mathematical formula must be understood in some other way. What was the idea? You are going to approximate, for example, y of t by using some delayed version or advanced version of x. So it's like this. Suppose you have two random processes, x of t and y of t. Now, you want to do something like this. X is very close to some alpha times x t plus tau. Of course, since the sign is changed, let me just use different one, beta x t minus that, something like this. Why do we need this? As I told you, as given as an example, sometimes people just watch what happens in the United States stock market and expect what will happen or anticipate what will happen in Korean stock market today. What does that mean? X is interpreted as, for example, Dow Jones Industrial Average. And Y is, in this case, interpreted as what? The Kospi. And of course, you may put some gamma if you want the offset, right? Because the Dow Jones and Kospi may have different offsets even after your delayed or fine approximation. And then you find best beta and gamma that minimizes what? This value. So it's kind of mean square approximation under a fine and delayed version. Of course, you can filter x because this is a single pass with delay, right? Since you've learned in signals and systems, how can you linearly transform x or affine transform x by using convolution with some function? You may later do something like this. You may find some h, right? So you linear time invariant filtering of x plus some offset. And now you know why we needed this one. As you've seen in neural nets, right? You always provide some constant so that the neural net can adjust. But anyway, so LTI plus some offset type thing, and you may put it there and approximate. In this case, this result is from what? A delayed linear approximation of y by using x. Got it? So you must interpret that way. Okay. Now here goes an example. So you check whether the previous lemmas are really correct. Actually, they are really correct. But anyway, let's check. The idea is simple. You have two jointly distributed random variables, A and B. And once you choose the value of A and B, you have full sample paths of x of t and y of t. See that? Capital A and capital B are realized, then x of t is fixed for all t, right? And x has in the in phase A, quadrature, negative b, and y has in phase b and in quadrature, positive a. Of course, as a communications engineer, possibly, you may want to write x of t as the real part of a minus jb times e to the j2 pi fct, f0t, and y of t as real part of b plus ja times e to the j2 pi f0t. Actually, after you get acquainted with this complex baseband notation, you can do much more than you just handle sines and cosines. Okay, anyway, so this is the idea, and you show some interesting results. For example, so here, suppose A and B are uncorrelated, zero mean random variables. Means that expectation of A and B are equal to 0, and expectation of AB also equals 0. So their random variables A and B, after taken, the expectation equals 0, and the product is also 0 after expectation is taken. So if you multiply x and y, what will happen? All the cross terms will disappear under this assumption. And again, to make matters more simple, we assume the second order moments are the same for A and B. And under these assumptions, this example asks you to show that two random processes are jointly wise and stationary. So you compute each random process is wise and stationary, and their cross correlation function is function only of tau. So you do it yourself. Okay. Now our focus is on covariance function, but it's too simple. You just subtract and take the correlation. So covariance function is correlation function after you subtract the mean path. That could be non-zero, that could be constant, depending on the condition. So here goes the definition when x is complex valued. Okay. And this is autocovariance, and this is cross-covariance when x and y are complex valued. For real random processes, we have the simple relation between correlation functions and correlation function and covariance function, and cross-correlation and cross-covariance functions. By the way, the variance of random process is simply what? As we've already seen, x of t minus mu x of t, magnitude squared, and then you take the expectation. Okay. And for wise and stationary random process, as we've seen already, autocorrelation evaluated as 0 minus mean squared becomes the power of the random process. Actually, the power, the covariance of the random process. And again, as I already told you, two real random processes called uncorrelated if cross-correlation function equals 0 for all t and tau, or correlation function equals mu x times mu y. Sorry, mu x of t times mu y of t. It's t plus tau mu y of t. Okay, for real case. If they are wise and stationary, you can further replace this functions of t with constants. Of course, again and again, independence implies uncorrelatedness even for two random processes. However, the converse is not true. Interestingly, if you have jointly Gaussian random processes, uncorrelatedness if and only if independence. However, when you have two complex valued random processes, then not just Y-sense stationarity, second order stationarity, that also assumes what? The complementary correlation functions, function only of time difference, is required. Be careful. So we've done for the correlation functions of real random processes, continuous time, real and complex random processes. Now, the definitions can be straightforwardly extended to discrete time, real and complex valued random processes. So I'm not going to repeat it. It's very easy. The only emphasis is on the case where your discrete time random process is obtained by uniformly sampling the continuous time random process. So the case is like this. So here you have continuous time random process x of t, and you have what? Sample at every t equals nts. Of course, you may assume some offset delta, but for convenience, we usually take delta as 0. In that case, we have xd of n defined as xc of nts plus delta if you want for all n. Now, so given this situation, very special case, okay? Not every discrete time random process is the sampled version of a continuous time random process. Be careful, okay? Some random processes are inherently discrete time as stock market processes. Anyway, so in this case of uniform sampled version of continuous time random process, the questions are like this. If continuous time process is Y-sense stationary, then discrete time is Y-sense stationary. What do you think? And if you remember, what is the definition and what could be the definition of mean paths of discrete time, continuous time random processes, autocorrelation functions, you may easily see that this is simply true because see that xd of n equals by definition xc of nts, which is what? Mu sub xc evaluated at nts. If xc is Y-sense stationary, this is mean of x continuous time for all t. Now, what is the autocorrelation correlation function of discrete time random process xd of m and n? By definition, this is xc of mts, xc of nts, right?
Dr. Joe, it is time to wrap up. Dr. Joe, it is time.
So this is simply continuous time random processes evaluated nts, and if continuous time random process is Y-sense stationary, it is a function of what? Time difference, m minus nts, which is the time difference between m and n. So obvious, just replace the discrete time signal to continuous time signal, and to have continuous time Y-sense stationarity implies discrete time Y-sense stationarity after a uniform sampling. Ready? And you can do a lot of things like what if x of c is strict sense stationary? Then its sampled version is strict sense stationary, something like that. You can ask a lot of questions all related to the stationarity, Y-sense stationarity, any order of stationarity, uncorrelatedness, orthogonality, blah, blah, blah. Got it? Okay, that's all for the day.